So this is our fourth video for Physics 12 for Chapter 1, and today we're going to take a pretty quick look actually at multiplying vectors. You don't actually need to know how to multiply vectors for anything in this chapter, but we spent a couple of days doing adding vectors and subtracting vectors, and I thought maybe we'll just put all of our vector toolkit in one place in your notes. And the first time you'll need to multiply vectors won't be until Unit 3, and then maybe again in Unit 4, and then not until Unit 7. So it's down the road, but it's kind of fun to take a look at it right now. So here we go. First thing to know about multiplying vectors is that there are two different ways of multiplying vectors together, and one of those ways involves using the dot symbol. So you may have had a teacher in the past use dots for multiplication. Well, it turns out they're actually a little bit different for multiplication of vectors than the cross symbol. So for a dot product, when you go and multiply these two vectors together, first thing to notice, that answer C, it doesn't have any arrowhead on the end, right? So it's actually just going to be a number. Now, if you grab two random vectors out of the air, they could be randomly long, right? One could be longer than the other. They could be pointing in different directions. And for multiplying vectors, it works really well to put those vectors together tail to tail. That's something that you never do for adding vectors. We always go head to tail. But for multiplying vectors, it's just really kind of nice. And it allows you to see the angle between those two vectors as they point in space. Okay, so how do you find the dot product between two vectors? Well, the deal works like this. You end up taking the size of A, multiplying it by the size of B, the length of B, and then you multiply it by the cosine of the angle that's tucked in between these two vectors when they're sitting together tail to tail. And that's it, right? This was decided by the mathematicians that that's how dot products would work, and it's always a cosine. So a couple of things to point out here. The answer is just a number. It's just a scalar. It's not another vector. And this theta that we're talking about is the angle in between the two vectors when they're positioned tail to tail. Now, cosine, if you want to get a good value for cosine, like the value of 1, that's the best it can do, you actually have to put 0 degrees in. So a 0-degree angle means that the vectors would be parallel, and that's the best situation for getting a good dot product. So final thing for our notes for this, for the theory part of the notes, dot products, they only give you a number, just a scalar. They don't give you another vector, and they do work best if the vectors that you're dotting together are actually parallel, if the angle between them is 0. That's the first half of the theory for today. It's a quick little lesson. I do have two examples you'll probably want to put in your notes, and then I think we should just take care of right now the 3 questions on the worksheet that we would typically do that go with today, and get it all done in the notes here too on the video. So examples for your notes. In Physics 11, we actually did do a dot product when we were calculating work. It was the only time we multiplied vectors together in Physics 11. And I want to just show you 2 examples. First of all, the easiest of all examples. What if you have a force and a displacement that actually line up parallel? So here's a person shoving a box down the road. And let's imagine that they push with 10 newtons of force to the east, and the box displaces 4 meters to the east. What you would do now as a physicist is you would imagine taking those two vectors, the force and the displacement, and arranging them tail to tail. Now, I've just drawn them like this. I guess if you put them tail to tail, they would be a lot closer, right? They'd be kind of like that. But then it kind of gets hard to see what's going on. So I just kind of move them apart a little bit. I just want to imagine that they're tail to tail and then think about the angle between them. Well, the angle between east and east is 0, right? These things are parallel. So the calculation would actually be 10, the size of the force, multiplied by 4, the size of the displacement, multiplied by cosine of 0, because these things are parallel. And cosine of 0 is 1, so we get 40 joules. Now you may remember this example from Physics 11. What happens if you're just carrying a box, right? You're lifting up on it so it doesn't land on your foot, and then you walk sideways down the road. And you had to remember the answer in Physics 11. It was kind of a special story that you just needed to know the answer for. But now you don't need to remember anything. In fact, let's throw some numbers in. Let's say that the force is 10 newtons up, so it doesn't land on top of you, and you walk sideways 4 meters to the east. If I take those two vectors, the F and the D, and bring them together tail to tail, I can see pretty quickly that the angle between them when they're arranged like that is 90 degrees. You don't have to remember anything about this story, just trust the dot product. You can go, okay, 10 times 4 times the cosine of that 90 degrees between those two vectors, And the cosine of 90 degrees is nothing. It's 0. And that wipes the answer out. And that's what you had to remember in Physics 11, that the answer was 0. Well, now the math does the thinking for you, which is actually quite nice. That is half of the lesson. Traditionally, there would be 3 questions on the worksheet that we would do for this day. I'm just going to actually do them right here in this video and just show you how they work. So this is now the homework. We'll just kind of get it done here together because it's so fast. Person pushes a crate 80 newtons to the west, and it travels 14 meters to the west. So if I was to draw those 2 vectors, I'd have my force going to the west and my displacement going to the west. And when I arrange them tail to tail, I can see that the angle is 0. So for work, I want to do force dotted with displacement. Okay, great. So I'm going to take my force of 80, multiply it by my displacement of 14, and then a cosine of 0 degrees. Always a cosine of the angle whenever you do a dot product. All right, I grab my calculator. 80 times 14, and then, hey, just for fun, I'll go times the cosine of 0. Cosine of 0 is just a 1. The 80 times the 14 is 1,120. Done. We'll call that 3 sig figs, and there's our answer. 1,120 joules. Okay, let's try a couple more out. The next 2 were as tough as you could ever get in Physics 11, and now I want to show you that they're actually pretty easy. A person's carrying a 27 kilogram box up a ramp, maybe like a wheelchair ramp kind of thing at a building, and the ramp's got an angle of 32 degrees, so it's actually pretty steep. And they travel 12 meters along the ramp diagonally. Okay, I'm just going to draw this person. So here they are, carrying this wonderful box up the hill. And it says they apply a vertical force of, getting technical here, 264.6 newtons. You know, actually all that is just a force applied upward to balance the weight. So 264.6, that's just equal to mg. So that would be down from gravity, and this person's applying that force up. Okay, so there's my 264. If you watched this box during the story, you'd see that it goes this way, right? It would displace diagonally along the hill, just like that. All we need to do, the hardest part of this question, is actually just thinking about the angle between the F and the D. It's not as bad as grade 11, where you had to take the D and do your SOHCAHTOA and break it down into components. It's actually really nice. And they said that this ramp's got a 32 degree angle on it, right? So, hey, that's 32 degrees. So just kind of thinking about angles in a corner, adding up to 90, that's going to be 58 degrees to make the full 90. Hardest part's done. If I wanted to try to find the work, I would just go F dotted with D. Okay, going to take my 264.6 multiplied by my 12 meters, and then always a cosine of the angle for dot products, and work is always a dot product. So a cosine of 58 degrees. No thinking required about the SOHCAHTOA. We can just trust the math, and it's going to steer us in the right direction. So 264.6 times 12 times the cosine of 58, and this story's over. 1,680, we'll call it. Okay. So no hard thinking required there, which is actually kind of nice. Hey, we're halfway. The other thing that we should take a look at is the other kind of multiplication. Oh, sorry, we're not halfway. We're halfway through those 2 examples that were hard from Physics 11. There's still this one, the person with the lawnmower. Okay, so got some lawn that we're mowing here. All right, there's the lawn, and we'll draw a little mower in here. Great. Doesn't even have to have wheels. It's fine. Got a handle on it. And this person is walking along, and they are pushing on this lawnmower, and it says that they kind of push down along the handle with this 35 degree down angle for the force. So yeah, they're kind of pushing this way, lining up with the handle. Force goes like that, and it says, oh yeah, it's 35 degrees down compared to the horizon. But the lawnmower actually just moves sideways across the grass, unless it's like quicksand. So the displacement's like that. And the hardest part of this question is already done. I was doing the drawing. Got a horrible looking person there pushing the lawnmower. They don't even have a neck. But that's okay. 35-degree angle between the F and the D, I am ready to go. I'm ready to figure out what F dotted with D would be, right, in order to find the work. I would take the force of 58, and then I would multiply it by the displacement of 17.5. Always cosine for a dot product, 35 degrees. And then just trust the math at that point, and it'll figure out the answer. So 58 times 17.5 times the cosine of 35, the angle between the two vectors. 831 joules, this thing's done. And with that, we are now halfway through the video, actually probably a little bit past halfway. We're going to move on to the only other kind of multiplication that's out there, and that is the cross product. Cross products are a little more interesting than dot products. When you cross two vectors together, you actually get another vector, right? You can see that little C with the arrowhead on it. So I have to show you how you can find the length of that answer vector and the direction for that answer vector when we do this thing called the cross product. Okay, it's definitely a third vector, right? So we do have those two challenges to go and find out size and direction. First of all, let me tell you about size. In order to find the size of the answer, which I'm just calling C, you would take the size of A and the size of B, your two vectors that you've got, you would multiply them together, and then you would take that product of those two numbers, and you would also multiply it by the sine of the angle between the two vectors when they're arranged tail to tail. So it's the same kind of thing as the dot product in the sense that you imagine them being arranged tail to tail. But this time we're going to use a sine instead of a cosine. That gives you the size. Now sine gives you 0 for an answer when you put 0 degrees in. So cross products don't like it when the vectors are parallel. You get nothing for an answer. But sine will give you a good healthy 1 when you put 90 degrees in. So it's the exact opposite of the dot product in terms of when you're going to get a big answer and when you're going to get a small answer. Maybe that's worth a quick little note here before we do direction. Cross products work best. They give you good answers, big answers, when the angle is 90 degrees. Okay, fine, we've got the size, but now which way does the answer go? For the direction, this is where it gets really interesting. The direction for the answer, if you were to cross these two vectors together, it's a direction that's perpendicular to A and perpendicular to B at the same time. And you might be looking at it going, that's not possible. Well, if you only think in 2 dimensions, it's not possible. But if you go outside the box and think in 3D, you could either have it come out of the page or into the page, and you would be perpendicular. You would be crossing both A and B. And so it's kind of picking up on that name, cross product. So to decide whether it's out of the page or into the page, we actually use something called the right-hand rule. There are a few different ways that you can actually lay out the right-hand rule. The one I like in particular, I found actually also on Google, the little picture of it. It's hard for you to draw this in your notes, but let me just show you the picture, and then I'll give you an easier drawing that you can put in your notes. But you basically take your hand, and you make like that crazy little, like gun shape when you were a little kid, making like a little gun with your hand, with your pointing finger being the barrel of the gun. And then you relax your middle finger until it points out of the palm of your hand. So every one of those first 3 fingers is pointing in a different dimension, in a different direction. That's a little bit tough to actually draw on your paper. So here's something that's a bit easier. Maybe just draw a hand, just kind of splotched down on your paper like that. And the deal works like this. Your thumb is always the first vector in the question that you have to multiply. So in this story up here, it was the A, right? But the first vector is going to be your thumb. The second vector is going to be your pointing finger. So the order that you're crossing them matters. And then your middle finger will show you which way the answer goes when those 2 first vectors are crossed together. That's it, but we're going to have some fun playing with this, with practicing this, so we'll do that in just a second. One thing you're going to need to be aware of, though, is that you're going to now work in 3 dimensions. So sure, you've got north, you've got east, and south, and west, but how do you draw a vector that's coming at you? Or how do you draw a vector that's going away from you? The good news is the mathematicians have figured out a plan for this. They said, imagine it's like an arrow. If you draw just a dot like this, that'll be the sharp end of an arrow that's coming out of your paper at you. So any little dots drawn on the page in Physics 12, that's a vector coming at you from your paper. If you want to draw a vector going into the paper, you actually draw an X. It's the tail feathers of the arrow actually diving down into the paper. Okay, so that'll be a vector going into the page. And that right there is the theory for this second half of the lesson. But we've got that worksheet that we can try out. So usually we get the worksheet all done on the same day that we do the theory. So I'm just going to put it right here in the video. It's question 7 that we would normally do. And this question says, hey, can you try to find the missing vector if it is a story of A crossing with B to become C? Now, it won't always be the letters A, B, and C in physics, but in this question it is. So if you imagine your right hand just kind of laid out on paper like this, as you look at it, when you lay your hand down on the page, because A is first, A has to be your thumb. And because B is second, it has to be your pointing finger. And then the answer is the third thing that you see there. So that's actually going to be your middle finger. And each one of these 6 questions is missing one of them. Now what I can't do is, in front of you, see whether or not you've actually got your hand pointing in the right direction. But you need to make that shape with your right hand and then try to get your hand moved around in space without kind of, flipping your fingers around. You have to just move your hand around in space until your thumb points this way at the same time as your pointing finger points up like that. And if you can get both of those happening at the same time, your thumb pointing to the right while your pointing finger points kind of the top of the page, you'll see that your middle finger actually points out of the page at you. So for the first question, the answer C comes at you, so we'll draw it as a little dot. There's vector C. Okay, let's try the next one. What do we have? You've got to get this to happen with your hand with these vectors here. So A is your thumb. You've got to have your thumb as an X. Oh, that's into the page. So stick your thumb kind of into your notebook while your pointing finger points up to the sky. Right? It's got to roll your hand around in 3 dimensions to get that to happen. And while your thumb points into the page in order to do this, while your pointing finger points to the top of the page, you're going to see that your middle finger actually points this way. Okay, let's try the next one. Oh, we're getting tougher here now. This one we know C, we know the answer. We know where your middle finger is pointing, but we don't know where your pointing finger is pointing. So for the next 2, actually, we're trying to look for that. Your thumb is coming at you while your middle finger points to the right. So thumb at you while your middle finger points to the right. When I try to do that with my right hand, it looks like I have to have that B finger pointing this way in order to get that to work. Question D is also one that's missing vector B. Your thumb has to point to the top of the page. And at the same time, while you keep your thumb pointing at the top of the page, get your middle finger pointing to your right. It's got to be your right hand. And then when you do that, it looks like your B finger is actually pointing into the page. So that would be an X for B. Okay, the last 2 questions, you're looking for vector A. So you're actually looking for where does my thumb point in order to get this to work. For question E, your pointing finger needs to point at you. That's a bit awkward. While your middle finger points to the top of the page. That one's actually almost painful. So your middle finger's pointing to the top of the page. Well, your pointing finger's pointing at your nose. And it looks like your thumb, I think, would go this way unless I'm making a mistake. And now the last one. B is your pointing finger. So get your pointing finger pointing to the left, and then C is your middle finger. It's got to go into the page, right? So middle finger's going in, pointing finger's going left. Looks like your thumb would be going down like that. So that would be A. And there, a little fun playing around with cross products just for fun, trying to see which way those missing vectors would go. It's definitely 3D, and the order is so important. The vector that comes before the cross, very different than the vector that's coming after the cross. But that finishes that video up, and we're all done having a little fun multiplying vectors together.